Sorry. Yeah, thank you so much. I'm keeping an eye on the chat, by the way, in case anyone wants to type anything in there. But yeah, so I'm Andrew Tawfeek. I just graduated from Amherst College in January, and I'll be starting in University of Washington in September. And this was my senior thesis work at Amherst. So I studied discrete gradient fields and Laplacians on simplicial complexes. And yeah, let's jump right in. So let me start off by first telling you what some of these words mean. So a simplicial complex is, in a way, a generalization of a graph, where rather than just having vertices, which are zero-dimensional, edges, which are one-dimensional, you then have faces like this, which are two-dimensional, and then you can have tetrahedra, which are three-dimensional, and it basically tries to go higher and higher. So we're going to need the formal definition, which is right here. So formally, a simplicial complex on n vertices, in this case n is 5, is a collection of subsets of 1, 2, all the way up to 5, that is closed under taking subsets. And by that I mean, if you have something inside your complex, so if we called our complex K, and we took this base right here, then 1, 3, 4 is inside K, and all its possible subsets are also inside K. So that's what the closure under subsets means. Furthermore, the elements of K are usually called cells or simplices. And to every cell, we associate its dimension. So in this case, this purple cell right here, I did not mean to erase that, has 3 elements inside it, 1, 3, 4, and we say it's a 2 cell. We go 1 less than the number of things inside that set. So this right here would be a 1 cell, this would be a 0 cell. And lastly, when you have some element of K, so again, let's just think of 1, 3, 4, and you have a subset of 1, 3, 4, so 1, 3, you say 1, 3 is a face of 1, 3, 4. And intuitively, it means this edge is a face of this 2 cell right here. And we usually write that as saying 1 is less than the other, as in like 1 is contained in the other. Now, this talk is going to be focused on the subject of discrete Morse theory, where you study these objects on called discrete Morse functions, which are functions on simplicial complexes. So let me explain to you what a discrete Morse function is. Given a simplicial complex like the one here on the slide, it's an assignment of real numbers to every single one of the cells that satisfies 2 conditions. And they look kind of scary at first glance. So all it says is it's an assignment that I did not mean to erase on to every single cell, such that if we focus on one of the cells, so let's do that now, and let's do this one slowly. If you focus on one of the cells, like we did right here, all its higher dimensional neighbors, at most one of them has a value that is less than or equal to the value assigned at sigma. So if this is our sigma here, its higher dimensional neighbors, well, it only has 1, it's this one right here, the value assigned to it is less than 20. So this first condition is satisfied, in that like there are no higher dimensional neighbors that have a lower value. The second condition says all its lower dimensional neighbors, so all the lower dimensional neighbors of sigma, at most one of them can have a greater than or equal to value. And we can see that here, both of them are less than 20. So the second condition is also satisfied. And you would go through and check this condition at every single one of the cells. So not fun checking rigorously, but thankfully we aren't going to be thinking too much about discrete Morse functions. We'll be thinking more about their gradients. I do want to mention one more very, very important thing, and that's critical cells. So in some cases, for some of these cells, both of these sets are going to be empty. And when that happens, we say those are critical cells. So for instance, if you look at 6 right here, you can ignore this top condition because the 0 cell doesn't have any any lower dimensional neighbors because 0 is as low as you get. But if you look at its higher dimensional neighbors, all of their values are higher than 6. So this set has nothing in it. And because of that, we would say that that vertex is a critical vertex. So why do I care about critical cells? Well, I will mention gradients first, I suppose. So here again, it's the same discrete Morse function. And let me explain to you how we get a gradient from it. So we point an arrow from one cell to a neighboring cell whenever we're pointing to something that's of lower value. So for instance, if you take this edge here, it has the value 20, its higher dimensional neighbor has a value of 18, so we would point an arrow like this. And we do these with all the possible cells. So if you look at this 15, its higher dimensional neighbor of having value assigned 13 would get an arrow because it decreases along as you proceed in that direction. And then we'd go through and then we'd just do this every single place. So 10 and 7. So it decreases along as you go that way. And then we'd put in all the arrows and we get left over with this. Now you might notice some of these don't have any arrows assigned to them. And that's because this doesn't decrease and this doesn't decrease. So in a way, this thing is like a local maximum. And so it doesn't get any arrows from either of the vertices. And coincidentally, well, not so coincidentally, the ones that don't have any arrows are the critical edges, and the zero cells that are kind of a sink are actually the critical vertices. So the gradients actually form an equivalence class on the set of all possible discrete Morse functions. And in particular, they preserve the critical cells. They tell you very concisely where your critical cells are. And the reason we care about critical cells is because of these two big inequalities that have analogs in Morse theory, which is the smooth version of this subject. And the inequalities say that if you let Ci be the number of critical cells in dimension I, so going back here quickly, we have that C0 is 1 because we have one critical vertex. We have C1 equal to 1, 2, 3, and C2 is equal to 0 because we don't have any critical two-dimensional cells. It says that Ci satisfies these two inequalities. The number of critical cells in dimension I is going to be greater than or equal to the ith Betti number. So this is the number of I-dimensional holes. So for instance, the 0th Betti number is the number of connected components. So how many connected bits are there to your simplicial complex? B1 is the number of cycles. So if you think of the case of your simplicial complex having only 0 and 1 cells, so it's a graph, then a graph like this would have a first Betti number of 1, and this would have a first Betti number of 2. So yeah, we always have this inequality. And then the second thing is the alternating sum of the critical cells is equal to the Euler characteristic. And these seem kind of odd, but they turn out to be extremely, extremely powerful and let you do quite a lot. And in fact, we'll be using them in a bit to prove some cool results. So yeah, so just keep these in the back of your mind. You certainly don't need to memorize them, but they are generally very, very important in the subject. So the objective going into the thesis was to understand the number of different gradients you can have. So a simplicial complex is a finite thing. There's finitely many cells. There's only finitely many ways you can throw arrows down on it. And only finitely many of those are gonna be, gradients. So the question is simple. How many gradients do you have on a given simplicial complex? Can you just count them all? Is it a nice number? Is there a nice formula? And that's what we wanted to try and find out. And what we ended up finding is this neat connection to this thing called the Laplacian. And this word might ring familiar if you're familiar with graphs, and it generalizes to complexes in a way I will describe now. So if you have a simplicial complex, so this is the same one from before, it has a bunch of groups associated to it, or you can think vector spaces instead, or if you want, you can go ahead and think of modules. But essentially, it has a bunch of groups corresponding to every dimension. So this being having at most 2 dimensions. So these are 0-dimensional cells, 1-dimensional, and 2-dimensional cells. For every dimension, we have this group, and this is the 1-dimensional one that is kind of like a vector space where your 1 cells in this case are your vectors and your coefficients are integers. As well as having these groups, we also have maps between these groups called the boundary maps. And they essentially send n cells. So if we took this purple subcomplex I have highlighted, they send those 2 cells to their boundary. So when we plug it in right here inside the second boundary map, it outputs what we intuitively think as the boundary of that subcomplex. And you might notice this is actually kind of a little cycler here. And that'll always be the case, that if you put something into the boundary map, its image is a cycle in 1 dimension less. So, and that's, you guys may have possibly run into the condition that this is actually a chain complex where doing one boundary map and then kind of composing it with the next one is always going to be equal to 0 because of this. But anyhow, so I mentioned that these can be sort of thought of as vector spaces. Therefore, these maps can be sort of thought of as linear maps or matrices. And then it makes sense to talk about having a matrix and its transpose and multiplying them together. And doing this is how you get the Laplacian in general. So if you were just talking about graphs, the first boundary map, when n is equal to 1, is usually called the incidence matrix. And this would be called, in that case, usually the graph Laplacian very explicitly. But yeah, so we can do this in general in any dimension. And we ended up finding a connection between this object and gradients, and specifically counting them. So let me explain the one-dimensional results, and then I'll kind of motivate how we were able to get up to higher dimensions. So I want you to kind of slowly try to piece together why what I'm eventually going to say is going to make sense. So if you have a gradient on a graph, so you know, a collection of arrows coming from just some discrete Morse function, then intuitively it makes sense to look at some subgraph of it, and you get a gradient induced on the subgraph by simply just removing everything else. Like that makes complete sense. Also, recall that the first Betti number is counting the number of cycles. So for instance, if here is C5, the cycle graph, it has a first Betti number of 1. And by one of the discrete Morse inequalities earlier, that means that whenever you put a gradient on a cycle graph, there's going to be at least one critical edge. So if you have a graph with a ton of cycles, every single one of those cycles is going to have at least one critical edge on its boundary. And the last thing I want you to notice is if you have a tree, and we gave that tree some gradient, so I'm just going to scribble very quickly a gradient on it, with the condition that there are no critical edges. So this gradient doesn't have any critical edges whatsoever. Then that implies, again, through the inequalities from earlier, that it's going to have only one critical vertex. So in this case, it'd be this one right here. And furthermore, just from the rules of how gradients are placed, it's going to be rooted at that critical vertex. So regardless how I would try to put a gradient on this tree, it's always going to be the case that all the arrows are going to point to a single vertex in the end. Now, using these three things, we're actually able to already say quite a lot. In fact, we've shown a bijection between gradients and rooted forests of the graph. And this is through the following fact, that if you have a graph and you give it a gradient, like right here, you're going to have some critical edges and you're going to have some arrows. And then if you delete all the critical edges, well, since there was one on every cycle, you just got rid of every single cycle. And then you're left with trees that don't have critical edges, and those are necessarily just going to be rooted. And yeah, and that's really it. That's the entire bijection, and you can likely see how it goes backwards. You have a rooted forest, and that gives you some gradient. But yeah, so we can actually say a lot more than this. So if we define this little set here, and this is all the gradients having k many critical edges, it corresponds just through the same argument above, the rooted forest having e minus k edges, and that's the weird minus thing is just because we subtract the critical cells. But yeah, so if we define the set here, we can use a very, very, very helpful theorem from graph theory. And it says that the determinant of the graph Laplacian, the coefficients of each of the lambdas is actually the number of vertices of all forests having I many edges. So you do need to think about this a little bit, but this is actually saying that all the Qi are corresponding to these sets we defined earlier. It's counting how many things are in there. Because if you have a forest, if you have some forest, so you fixed the forest and you counted the number of vertices in that forest, that's basically like counting every single way you can root that forest. And yeah, and because all these sets are disjoint, if you plug in lambda equal 1, you end up essentially summing up all these sets, and it gives you the total number of gradients on your graph. And yeah, so we managed to count all the gradients on the graph, and it conveniently had this nice little connection to the graph Laplacian. So how do we go any further? So This part is gonna get slightly technical and it was slightly messy, but I'll try to motivate why things happened the way they did. So first we need to kind of come up with a conjecture. What is it supposed to look like? Well, you start thinking about the default Laplacian and think about what it should know. So it's the dth boundary map and its transpose. The dth boundary map is the map that tells you how the d-dimensional cells are connected to the d-1 dimensional cells, and then it's transpose. Um, but it doesn't know anything else. It doesn't know about d-2 cells. It doesn't know about d-5 cells. It doesn't know what happens outside of dimensions d and d-1. Um, so in a sense, we're ignoring everything that occurs in much lower dimensions. And how did we ignore things in one dimension? Well, we just said, oh, those are going to be the critical cells. We're going to delete the things that are critical. We're essentially not going to know anything about them. So now we can kind of redefine and kind of define a generalization of those sets we defined earlier, where we're going to say that the subscript is now, basically you're just going to be looking at cells being non-critical in dimensions d and d-1, where everything else under that is critical. We don't know what happens below that. We just know that there are some non-critical cells in dimensions d and d-1. And then it's just natural to think, why don't we just have the same thing? I mean, I feel like this is where we'd always naturally go, just like maybe it's just the same formula. I mean, I don't know. It was kind of out of pure laziness, just hoping, what is it, that it doesn't get any more complicated. But things, what is it? It turned out to surprisingly, what is it? To surprisingly work out well. But things got complicated because rooted forests in higher dimensions for like a higher dimensional simplicial complex aren't as simple as they are for graphs. For graphs, you have a bunch of edges and then you only have like, basically you have no cycles and then you have a root, which is always a single vertex. In the higher dimensional case, so this is the case for 2 dimensions, your root can be very messy. So a forest in higher dimensions has to satisfy the condition that there are no 2-dimensional holes. And a 2-dimensional hole is a cavity. Oh, sorry. Oh, yeah. And yeah, so you're not supposed to have any 2-dimensional holes. And a root can essentially contain multiple things. I won't go into the specifics of the root unless someone asks, but yeah, your root can essentially contain a lot of cells, and it can also noticeably contain cycles within it. And the analog of the theorem we had before is also kind of a fair bit more complicated, because now there's these weird terms showing up where you have to take into consideration this notion called torsion. How weirdly twisted is your complex? Like, for example, think of a Mobius band or a Klein bottle. Those are things that weirdly are, I guess the technical term is non-orientable. And that causes problems in higher dimensions. And as you can see, this is all fairly recent in that like people are still trying to grapple with how to exactly count and think about these things in higher dimensions. So I will jump ahead a small bit and say, after a fair bit amount of work, we were able to figure out that our formula from before does actually hold. And in fact, it only holds when we're thinking about or triangulations of orientable things. So if you have, say, a sphere, a triangulation is exactly what you think it is. It's basically drawing triangles on it, and those would be your vertices and edges and faces. And this would be your simplicial complex. And when that's the case, the formula does hold. And whenever it's non-orientable, so like a Klein bottle or a Mobius band, any possible triangulation of that does not work. And yeah, we were able to prove both these things. And yeah, all right, got a bit ambitious, but